The next thing we are often asked to do when it comes to functions is to put more than one function together. A function that is defined by two or more equations over a given domain is what we call a piecewise function. That is, it's in pieces. Now, when we're asked to evaluate the following function, f, notice the function has got these little brackets or braces, and it says that x squared plus 1 is the function as long as x is less than 0. But when x is greater than or equal to 0, the function looks like x minus 1. And they want us to evaluate for x equals -1, 0, and 1. It's one of the same things where it's like, okay, now the domain's been restricted to one or the other, sometimes even more functions, based on some restrictions. So if it's less than 0, I have to use this. If it's greater than or equal to 0, I have to use the second one instead. So when you have numbers like -1, 0, and 1, I can't just start plugging them in everywhere. -1 can only go into one of these two. For that matter, if x is equal to -1, which of the two equations will that fit into? It's going to fit into the top. So when x is equal to -1, I have x squared plus 1 as my function. That is -1 squared plus 1 as my function. That is -1 squared is 1, 1 plus 1 is 2. If you plugged it into the other one, you still get an answer, but it won't be the correct answer because it's not allowed in that domain. Next, we have 0. Now this one's tricky. When x is equal to 0, both of those talk about 0, but which function is it defined for? Which one of those two portions or pieces of my function can I use x equals 0 for? That would be the bottom one. So when x is equal to 0, I can only use x minus 1. Now, x minus 1, that means 0 minus 1. That means that when x is equal to 0, my function value is -1. And then last but not least, I have 1. So when x is equal to 1, I have to use the one that says x is greater than or equal to 0. I'm going to use x minus 1 again. That is 1 minus 1. That is when x is equal to 1, this function is equal to 0. When it comes to piecewise functions, the important thing to do is to literally make a table of values for each one. So let's take a look at both of these. So x squared plus 1. So first I have x squared plus 1 as my portion of my function. And I want to know what the y values are equal to, or my function values are for these. Now, it tells me to go values that are less than 0. So you might want to do something like -2, -1, and even though it says less than 0, you should still look and see what's happening at 0. And we're going to take a look at how that turns out when we're putting both of these together. So we go -2 squared is 4, 4 plus 1 is 5. I go -1 squared, that's equal to 1, 1 plus 1 is 2, which we had down here. And then last but not least, 0 squared is 0 plus 1 is 1. Now I also know that that was not defined in there, but it's going to show up when we put the two together in just a second. For the other one, let's make a table of values again for x minus 1. This time my function values for x minus 1, as it defines it here, are greater than or equal to 0. So I'm going to start at 0 and maybe go 1, 2. So 0 minus 1, 1 minus 1, and then 2 minus 1. So that's what my table of values looks like for both of these. When it comes to piecewise functions, and this is the tricky part of it, make a little bit of room here. Look at what happens when I graph both of these on the same coordinate system. The biggest number I have out of both of those tables is 5, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Just make 5 all around. There's method to my madness here. I am using purple because I'm about to combine both the red and the blue graph. There's your art lesson for today. We take a look at the red. The red looks like x squared plus 1, so at -2, positive 5. -1, positive 2. And then 0, 1. At 0, 1, though, it says less than 0. I cannot use 0, 1. But at 0, 1 instead, if you remember from graphing inequalities, all you have to do is put an open circle there. That's what tells me that I can go all the way to 0, 1, I just can't use it. And then I connect those with a dot, and if you remember a little bit about these types of graphs, this is portion of a parabola. Then for the next one, I have x minus 1, that's the blue. That is 0, -1, and now for the bottom equation, it is allowed to be equal to 0. So 0, -1, I can use a solid dot. Then I go to 1, 0, and then 2, 1. A little sloppy on the graph, but that's fine. Remember, it starts there and it keeps going. So notice my piecewise function is two portions of the same, on the same function, two portions of a graph put together. It looks like this broken up piece of an equation. It's still a function because even at right here on this open circle, it did not repeat because that's not included in the red, but it is included in the blue. All right. So piecewise functions is just two or more equations that together form a new portion. Now for the application types, I always like ending a lesson with applying it to more real-world type situation. In this case, and this is pretty standard, that the ratio of the height to the radius of a soda can is 4. Now write the volume of the can as a function of the radius r. It's kind of cut off a little bit, but that's fine. That is, in this case, in order for us to be able to solve this, and to work with equations, we want to have just one variable. We can't necessarily graph using more than one variable in this case. In order for it to be a function of a variable, we have to be able to relate one to the other. So they want us to relate this as r. So we're going to start off with, for part A, our equation for volume. First of all, the volume in terms of r. Volume of a can, the equation is pi r squared h, that is the volume of a cylinder. But the volume in terms of r for part A, we're going to take h out of this equation. Now they told us right here that the ratio of the height to the radius is 4. That means ratio of, so as it says, h over r, this ratio here is equal to 4. That means that h is equal to 4 times r. Or, if you would like to place it the other way, that means that r is equal to h divided by 4. Those are the two ways that h relates to r and r relates to h. Now, in order for us to have just one variable, we have to do some substitutions. So they want a function of the radius r. That means that I have to get rid of h. So in part A, I'm going to say volume in terms of r is equal to pi r squared. Instead of h, I'm going to use a substitution for h. h is equal to 4r. Simplify this out, and I get V, the volume of a can in terms of its radius, is equal to, and then 4 times r squared ends up being 4 pi, and then r times r squared is r cubed. So now if I know the radius, I know the volume of the can of soda. I don't need to measure the height. Likewise, let's say you know the height of the can of soda, and that's part B. Part B is now asking you, write the volume of the can as a function of the height instead. That is for part B. If you want to try this one out on your own, this would be a good time to pause. But for part B, we are looking for the volume in terms of its height. So if you want to try it, go ahead and pause. If not, let's take a look. So pi r squared h again. But in terms of h, I don't want r, so I'm going to have v in terms of h is equal to, I'm going to substitute for r, and we said here earlier, r was equal to h divided by 4. So I'm going to say h divided by 4 squared times h again. All we got to do is clean that up a little bit. So h squared is, and then times h, and then pi, nothing to do with that, and then 4 on the bottom squared ends up being 4 squared on the bottom still, 16. And h squared times h is h cubed. And for good measure, leave the irrational number off to the side. So the volume in terms of the height is equal to h cubed over 16 times pi. You can rearrange those values. You can put pi at the top with the h cubed, not a big deal. Completely up to you. All right. Next, the path of a baseball is given by the following equation. F of x is equal to negative 0.0032 x squared plus h plus 3. Will the ball clear a 10-foot fence when it's 300 feet away from the batter? All right, so now the ball follows this path. This path is that of a parabola, anything that flies through the air. Those of you in physics, you're going to learn a little later on that anything that flies through the air follows the path of a parabola. That is, it's symmetric on both sides at some point through its rise and fall. But in this case, as the ball is going up in the air and coming back down, it's going to follow this equation. The question is, will it clear a 10-foot fence 300 feet away from the batter? A hint for you guys, f of x is the ball height. That is, the y value is how high it is. X is the distance from the batter. All right, so if you want to try this one out, this would be a good chance to pause. If not, take a look at how we would approach this one. We would say f of x. X is the distance, and the distance is 300 feet. I'm looking for f of 300. That is negative 0.0032, and then 300 squared plus 300 plus 3. All right, so we calculate this. What is f of 300? What is the height at 300 feet away? So these numbers look pretty bad, but there is method to that madness. This right here, after we clean this up, 300 squared is 9 with 4 zeros. And that's going to bring that way back down, plus 300 plus 3. Bottom line, when we clean all of that up, we end up with 15. All right. So, question is, will the ball clear a 10-foot fence when it's 300 feet away from the batter? Well, how high is the ball 300 feet away? It is 15 feet in the air. Will it clear a 10-foot fence? The answer is yes. So it's all about interpreting the input-output values in this case. The path of the baseball, that is telling you the height of the baseball as it's traveling. 300 feet away, that's the x value. The height then becomes the y value. And 300 feet away is 15 feet in the air. It will clear the fence. The last thing that we have in this section is probably one of the first true concepts of calculus, and something that you're going to be learning a little later on and using again in calculus next year. But first of all, it's what we call the difference quotient. That is, the difference quotient is a way to take derivatives. It's a more advanced mathematical concept, but for now, we're going to work on the side of the algebra side of things for the difference quotient. That is, if you have two functions, or one function such as f of x equals x squared minus 4x plus 7, the difference quotient of that function is where you plug in an x plus h in place of the function, and then you subtract the original function from it, then divide the whole thing by h. Now I know that sounds a little weird, and it's might even just look strange right now, but the one thing you want to do is in this function, instead of saying x squared plus 4x plus 7, that's f of x, we need to also define what is f of x plus h. That is, every time you see an x, you're going to replace that with x plus h. That is, instead of saying x squared, you're going to say x plus h squared. What is x plus h squared? That becomes a FOIL problem, where you have x plus h times x plus h, and go through all the FOIL and all the stuff we learned in algebra. We end up with x squared, and then x times h is xh, h times x is xh as well, so 2xh plus h squared. So that's a little bit weird, but take a look at what happens next. So then for the next part, x plus h squared becomes all of this. The other one was negative 4. Instead of x, I'm going to say x plus h. There's a reason why I'm doing this. I'll show you in a minute. This becomes negative 4x minus 4h. And then the plus 7 I don't have to do anything for. But look at what happens here. I'm supposed to say f of x plus h, which is all of this, and then subtract f of x from it. So just to show you what happens in this case, we start off with what we said there, x plus h squared, which I went ahead and got you a number for that, an expression, minus 4, and instead of x, I'm going to say x plus h, based on this equation here. Then plus 7, because there's nothing different, it's just plus 7. Subtract the original, which is all of this, and then when you're done, you're going to divide by h. Alright? The nice thing about this is I went ahead and actually worked this out on the side so you can see it kind of spelled out a little bit, but it's quite a bit. There's the x squared plus 2xh plus h squared, then minus 4x minus 4h plus 7. Also notice there's something else going on here. This is minus all of that, so that becomes minus x squared minus you have to distribute. So minus 4x becomes plus 4x, and then minus the positive 7 becomes minus 7. Don't forget that, or the whole thing is not going to work out. Because if you're looking right now, it's like, oh, there's too much going on. But if you start looking a little closer, you're going to notice a few things here. X squared, and then minus x squared cancels. Minus 4x and plus 4x cancels. And there's a lot of stuff that just drops off, such as plus 7, minus 7 cancels. You know you've done this right up to this point if a lot of things start to cancel as you're working through this. So look at what that simplifies to. The 2xh, the h squared, and the 4h simplify. All of that divided by h. And now something else is probably standing out to you. And you're like, wait a minute. They all have an h in common. So I can divide an h out from everything. H will cancel here. H will cancel there. Does not cancel with the one inside because I moved it to the front. I already took the extra one from the squared. And so my final answer using the difference quotient is 2x plus h minus 4 as long as h is not equal to 0. And we say that again because in the very beginning I was dividing by h. So again, this is called the difference quotient. You're going to get to use this in a little more detail at a later point in pre-cal and even in calculus. For now, we need to focus on the algebra behind it. So if it seems a little bit confusing, just know that this is a little more advanced of a concept. Right now, I just need you to focus on the algebra side of things. All right, so that brings us to the end of section 1.4. You do have a homework assignment that is tied to this lesson. This is the textbook problems that you're going to be working on. However, these are found on WebAssign. I want you to complete the WebAssign problems. It's going to give you several opportunities to try these out. It is the same exact problems that is on the textbook if you want to see them, but I want them completed on WebAssign.